Well, good afternoon. What I want to talk about today is the risk of seismicity associated with the injection principally of wastewater. And my day job is actually working with a very talented group of researchers on sort of the upstream challenge of oil and gas development from these unconventional reservoirs. And it's a challenge indeed because of the low permeability and the other complexities that Jim Brown was discussing. The reality of the situation is that while this is an energy revolution, and the gas revolution is upon us, the oil revolution, the tight oil revolution is occurring as we speak, but we're not very far along. We're not anywhere close to where we'd like to be. We're only recovering about 25% of the gas and maybe as little as 5% of the oil. So we need to do a better job. And if we do a better job, it's good as, from a perspective of resource development. It's certainly good from the perspective of the impact of the development on the environment. And, there's no question that horizontal drilling and multi-stage fracking is a large-scale industrial process, and we've been talking about all of the different environmental impacts, and I'm going to focus on the issue of earthquake triggering. Now, in 2011, I was asked to write a paper for the general public on what seemed to be a flurry of triggered earthquakes that were occurring. A couple of earthquakes of note had occurred in Youngstown, Ohio, one on Christmas Eve and one on New Year's Eve. The Dallas-Fort Worth Airport had become seismically active in 2006 and had kept producing earthquakes. A sizable earthquake had occurred in the Raton Basin and one in central Arkansas. And so this was of great concern, and I discussed this issue in this paper in 2012. No sooner was the paper out then a group of investigators argued that a magnitude 5.7 earthquake, the locally pronounced Prague earthquake in Oklahoma, had been triggered by triggered seismicity. And I'm going to talk about Oklahoma at some length here in a few minutes. Now, we have to recognize that there are approximately 150,000 EPA Class II wastewater injection wells that have been operating with little incident for many years. And so, this is not anything new, but the rates of earthquakes have increased dramatically, and the amounts of injection have increased due to the injection of the flowback water as has been described. So the first question we have to be asking ourselves is this really something, to worry about? And the answer is yes. And regardless of where we look around the world, we see that earthquakes are occurring all the time as a natural geologic process. So we focus on the plate boundaries where the really big earthquakes occur, like along the San Andreas Fault or the subduction zones that plunge beneath Japan and South America, Southeast Asia, and elsewhere. But the forces that drive the plates are transmitted through the plates, and those forces produce earthquakes from time to time. And you probably can't see it on these maps, but there are red dots on the maps, and that's where dams have been built, reservoirs have been impounded, and earthquakes have occurred as a result of a very small pore pressure perturbation due to the impoundment of that reservoir, which means that those natural faults in the earth were close to failing anyway, and that little perturbation set them off. So this is an issue to be concerned about. And even in relatively low seismicity areas like eastern China, some of the biggest earthquakes, most devastating earthquakes in history have occurred, and there have been any number of reservoir-triggered earthquakes. So this happens worldwide. Now, I'm pleased to talk about this because this is where my career began, about the same time as Jim Brown's. And my children tell me that if I held on to those sunglasses, they'd be back in fashion. But hydraulic fracturing can actually be used to measure the forces in the earth. And that's what I was doing here in the mid-1970s in the western Mojave Desert when I left my PhD in the laboratory and went out into the real world. And so it's nice to bring these topics back together. Now, this animated slide comes from Southwestern Energy, who employs much better graphic designers than I do. And what they're illustrating is the process that was just described: horizontal drilling, multi-stage fracturing, tiny little micro-earthquakes. These micro-earthquakes are about magnitude -2 in size. That shouldn't mean much to you, but it's about a patch of a fault that's about 1 meter across. It slips about 1/10 of a millimeter. So tiny, tiny little events that you would never know occurred if you didn't have seismometers down in a nearby well. But at the same time, there are natural faults in the earth that are nearby, and those faults are going to produce one of these intraplate earthquakes at some time in the future. And the problem occurs due to wastewater injection. And so normally we inject wastewater into a suitable horizon, isolated from the biosphere. Everything is fine. But every now and then, one of these wastewater wells will intersect some pre-existing faults that will connect up to one of these basement faults. It lowers the normal stress. It lowers the stress acting perpendicular to the fault, which is the stress that kind of keeps it clamped shut. So you simply unclamp that fault and allow an earthquake to occur now, as opposed to an earthquake that would have occurred, say, thousands of years from now. So you're advancing the clock on a natural process. And this has been happening a lot. So this map shows the Barnett Shale area. The red dots are earthquakes that have been occurring since 2006, and the yellow dots are the injection wells, the high volume injection wells. And as you can see, there's a cluster of high volume injection wells near the densest cluster of earthquakes. More recently, another area near Fort Worth has lit up near Azle, Texas, and in 1 week in November, there were 7 earthquakes. And here's a news report from Elsie Ann Ponte, the assistant to the police chief, and she said, "Oh, earthquakes, that's good. I was afraid it was Godzilla." And this cartoon, you can't read the caption, but it says, "Oh, good, Godzilla. We thought you said Quadrilla." Now, for those of you who know, Quadrilla is the company that's been drilling and fracking in England with much controversy. So, you know, Godzilla is now in high esteem compared to, you know, hydraulic fracturing and triggered earthquakes, I'm sorry to say. Cogdell, Texas, also in September 11. This is an EOR project. CO2 was being injected and earthquakes were being triggered. Again, the biggest being a magnitude 4.4. Timpson, Texas in 2012, magnitude 4.8. You know, these earthquakes are being very widely felt. Under very rare circumstances, they might cause a little bit of local damage, but everybody is aware that they're happening, and they are very disturbing. If you've ever been in an earthquake, even a small one, you know, it's a very disconcerting thing to go through, and people are naturally worried. My colleague Bill Ellsworth at the USGS prepared this map of the central and eastern United States and this earthquake count. And what you can see is that the rate of earthquakes occurring was more or less constant to about 2000. Then there was a small increase, but starting in about 2009, the rate of earthquake occurrence throughout the entire central and eastern US really took off. Now, I was asked to brief the governor of Oklahoma last spring, and I put a bunch of data, which I'm about to show you, together. And of course, she was interested in what was causing the earthquakes, and it was very hard to be definitive. And so I sort of entitled my presentation, as you can see, The Curious Case of Oklahoma Seismicity. And I'll present why it's a curious case to you. Now, this map shows in blue dots earthquakes that have been detected at more or less the magnitude 2.5 and above level. That means we think the seismic networks are not missing anything. So the catalog is complete. And as you can see, in a 34-year period, the blue dots are occurring all over the state of Oklahoma. And there were 4 magnitude 4 or larger earthquakes in a 34-year period. Some of these might be related to oil and gas operations. Some of it might just be background intraplate seismicity. But in the 4 years between 2009 and October of 2013, the red dots have appeared. And as you can see, they're also distributed all over the state and quite intense in the area just east of Oklahoma City. And of course, the Prague earthquake was part of that sequence. There were 9 earthquakes in this 4-year, 9 earthquakes of greater than magnitude 4 in this 4-year period, and the state of Oklahoma refers to basically a 30-fold increase in earthquake activity in the state in just a 4-year period. This is what it looks like if you count the earthquakes. The blue line are magnitude 2.5. The black line is the magnitude 3 and larger. And the red line indicates that Prague earthquake, so it locally increased the earthquake count. But even without the Prague earthquake, you can see the line increasing markedly in the period since 2009. Now, in many ways, the increase in seismicity appears to be a natural geologic phenomenon. The seismicity is regionally distributed. It's not localized in a particular oil field or near any particular injection wells. And the earthquakes are statistically similar to natural earthquakes. We know that for every magnitude 5 that occurs in a region, there are 10 magnitude 4s, 100 magnitude 3s, 1,000 magnitude 2s. We've made this observation all around the world. That is also true in Oklahoma, and the state of Oklahoma is now, their position is, things are going on, we don't fully understand them, but they're leaning toward interpretation of the phenomena as a natural geologic process, and that may well be right. So we should ask ourselves, however, whether injection pressures and injection volumes have been increasing through the state. That might help us explain this. Now, this shows data from the state of Oklahoma on average pressure on the top and the number of injection wells on the bottom. So there are about 12,000 wells injecting water in the state. The area shaded in pink is where the data is incomplete. And I literally received on Thursday the update of this water database to help us with our research. But as you can see, there's been no change in pressure for roughly a decade or so. So it's not like the state is sort of pressuring up that we can see. There has been a steady increase in the volume of water. So these are monthly averages, and it's a logarithmic scale. So you can see there's probably been a factor of 3 or 4 steady increase since the late 1970s. But a lot of these wells are involved in enhanced oil recovery. So they're just cycling water in a reservoir. And we've, on Thursday, received the data that will allow us to separate out the saltwater disposal wells, which then result in a cumulative increase in water, and we'll see what that data show when we are able to analyze it. And frankly, it's not very plausible to argue that the entire state has sort of reached the tipping point all at the same time. So, is it a geologic phenomena? Are there triggered earthquakes? Are both phenomena going on? We simply don't know yet. Another test is whether or not the location of the large volume injectors throughout the state correlate with the areas of recent seismicity. And that is now shown in yellow. The blue dots are the old earthquakes, the red dots are the recent earthquakes, and the yellow dots are the high volume injectors. And you can see there's no obvious correlation. In fact, you can convince yourself there's almost an inverse correlation. The earthquakes are occurring where the injection does not. Let's take a closer look at Prague. And as you can see, this church was pretty severely damaged. There was other damage. Fortunately, no one was seriously injured. But a magnitude 5.7 earthquake is certainly capable of causing damage to poorly built structures that are in the vicinity. This again shows the recent seismicity, and this lineation off that you see on the right side of the slide is the sequence. There were actually 3 earthquakes larger than magnitude 5, the largest of which was 5.7, and there's one injector well in the area. Was that responsible for these earthquakes? Well, we just don't know. There are a lot of other injectors around and a lot of earthquakes where there are no injectors. The interesting thing about Prague is that one of our fine Stanford PhDs, Katie Karanen, was a professor at OU, and when the first earthquake occurred, she rushed out and put out a seismic network that allowed her to determine accurate locations and depths for the aftershocks of the first earthquakes, as well as catch earthquakes 2 and 3 and their aftershocks. And what you can see in this cross-section is that while they were injecting into the sedimentary rocks in the overburden, which is basically the Arbuckle formation, a very porous saline aquifer, the earthquakes were occurring in the basement rocks. So they were triggering slip on faults in the crystalline basement rocks. And this is very important because you can only get large earthquakes on large faults. If we look at what happened in Guy, Arkansas, where wastewater was being injected associated with the production of the Fayetteville Shale, a seismologist from the U.S. Geological Survey, Steve Horton, put out a seismic network. He was able to show a lineation of seismicity, and again, a migration of the seismicity away from the injection well, and again, into the crystalline basement rocks. So what we're beginning to see is that the earthquake risk depends on whether or not the injection at shallow depth is communicating with these potentially active faults in the basement. Now, we know how to manage this, and that was the subject of the paper in 2012, and I borrowed from the geothermal community kind of a stoplight system. You know, everything looks fine, something's going on, let's make some additional measurements, or what's going on looks problematic, perhaps we should stop or at least change operations. So the first element of managing the risk is to avoid injection into potentially active faults. Now that's a no-brainer, but in these 150,000 wells, site characterization was not a criterion in any one of them. So basically, you know, almost all of them were located in relatively safe places, but a few of them were not. And we know how to solve this problem. We looked at it in the Teapot Dome area of Wyoming as a scientific experiment, trying to understand whether a pilot CO2 project could go on. And so we looked at the forces, which are the red arrows. We looked at the faults using seismic data. And we asked the question, you know, could these faults move if we change the pressure? And the answer was, in some cases, in the ellipse, the red ellipse, those faults would not be able to sustain a change in pressure. So you would not want to inject there. The faults enclosed in the green ellipse was just the opposite. They were perfectly stable, and you could have gone ahead and changed the pressure without any problem at all. We know how to solve this problem. We never take time to do it, and often don't have the kinds of data available, but it's not, you know, it's not something which is all that mysterious. So if we avoid injection into potentially active faults, we limit injection rates, we monitor the seismicity so we know what's going on, we can assess the risk. So now let's look at this Guy, Arkansas case. That lineation in seismicity that I showed you before defines an active fault, which in a force system that we know quite well because we've been studying the earthquakes just to the north and east of there. This is a region where 3 enormous earthquakes occurred in 1811, 1812. So the north central Arkansas is an area prone to earthquake activity. And when we look at the details of the fault, we see it looks just like what one might expect from first principles in sort of an introductory structural geology book. So we knew something was happening that was worrisome. And in fact, the Arkansas Oil and Gas Commission then imposed a moratorium on injection, and we have to be prepared to abandon some injection wells. And that moratorium covers about 1,000 square miles. Now, is that solution required? Well, it solves the problem, but not only does it raise the cost, it's caused an awful lot of truck transport to haul all this water off. And are those wells, you know, located in the right place where it's being taken to, or is it only a matter of time? So moratoriums, they can do the job, but it's, you know, it's kind of like you know, a meat axe approach to the problem. And by understanding the science, we can be much more strategic. Another thing we have to remember is the importance of water recycling. There's effectively a moratorium on injection in Pennsylvania, not because of triggered earthquakes, but because there are no good saline aquifers to inject the water into, and hauling all that water off to Ohio to find better geology was really not a very you know, a good thing to do. And in fact, the Youngstown earthquakes were triggered by injecting water, and perhaps they thought just because the truck drove over to the state line, it was now safe to inject the water, when in fact they should have gone further west and gotten into better geology. But water recycling is a good thing. You use less water, and of course, you don't wind up having to re-inject it. So what we're doing now is we're actually trying to come up with a site characterization protocol. 8 of my colleagues and I at Stanford are working with 12 companies right now to kind of try to take a scientific look at this question, kind of along the lines of what was discussed this morning with respect to methane leakage. If we understand the problems, what data can we obtain to manage the problem with the least disruption to activity and still protect the public? And our first meeting will be at the end of this month, and we hope by midsummer or so we'll have this protocol available, and we'll be able to share it with the public. So this triggered seismicity is a real issue. It's a big issue. It's an issue that's been growing in importance and public concern for the last couple of years, but it's an issue that we understand, and I think it's an issue that can be effectively managed. We simply have to be much more aware of it and much more proactive about preventing the problem before it occurs, rather than simply react to it, in which case every earthquake that occurs is being claimed to be an induced earthquake in the eyes of those who are opposed to shale gas development, and none of the earthquakes are caused by injection in the eyes of those that are promoting it. And that's not the place to be. There's a scientific middle ground, and I think we can get there. Thank you very much.